Hello everyone, my name is Lian Chen and I am excited to present our CVPR 2023 paper, Learning the Distribution of Errors in Stereo Matching for Joint Disparity and Uncertainty Estimation. The code is available on GitHub. In our work, we present a novel joint estimation called SetNet, which is stereo error distribution network that enhances not only the performance of disparity prediction, but also the estimation of aleatoric uncertainty. We introduce a new approach to approximate disparity error and uncertainty distributions using differentiable soft histogramming technique. Additionally, we propose a matching error loss based on K-out divergence, applying to the histograms generated by the above technique to enhance the precision of uncertainty estimation. In stereo matching networks like GCNet, GWCNet, and PSMNet, disparity maps are produced by constructing and processing a coarse volume from stereo image pairs. Since this process is imperfect, uncertainty estimations are valuable. Recent studies, such as refractive confidence network and coarse volume analysis network, have demonstrated the advantages of jointly estimating both disparity and uncertainty or confidence through multitask learning. Here, we distinguish between confidence and uncertainty estimation. Confidence refers to a probability or likelihood of correctness and usually trained with binary cross entropy loss when using a reject threshold to build binary mask. While uncertainty is related to the magnitude of the expected error of an estimate and often checked in regression mode. Both formulations cannot predict the magnitude of the errors. But we can predict the uncertainty per pixel following the work of Kendall and Gale. A fixable object is to train an uncertainty estimator whose outputs follow the same distribution as the true errors of the disparity estimator. We start with a quick review of the negative log likelihood loss proposed by Kendall and Gale that also estimates the aleatoric uncertainty per pixel. The numerator is the disparity error, while the denominator and the regularizer refers to the uncertainty. For numerical stability, we train the network to predict the log of uncertainty scalar. Mismatching between the error and uncertainty occurs when only train the network with NLL loss. Instead, we propose to additionally learn the distribution of errors and then supervise the uncertainty estimator via K-out divergent loss to enhance the precision of the uncertainty estimation. Here is the overview of our proposed SetNet. We use GWCNet as our stereo matching backbone and it interfaces with the novel uncertainty estimation subnetwork. During training, we output disparity and uncertainty maps and also compute the error maps at multiple resolutions. While in testing, we only keep the highest resolution. For each pixel, we compute the square differences between disparity estimates at different scales to form the corresponding pairwise differences vector. Our uncertainty estimator is a 3-layer MLP that takes the PDVs as inputs and predicts the multi-scale uncertainty maps. Now we start to discuss our matching error loss. We first need to prepare the inputs by building the distributions of errors and uncertainty. To get the distribution, an effective approach is to construct a histogram of the errors. Maximum likelihood estimation can be used to approximate the probability density function of the distribution, but it's not differentiable. Hence, we use the soft histogramming technique. Firstly, we pick n bin centers based on the mean and standard deviation of the errors. Given the error of pixel I, which is EI, we compute the L2 distance between EI and the bin centers. We convert the distance into pixel weight by an exponential function. Applying softmax to the pixel weight of a specific bin allows us to transform them into contributions corresponding to the center of each bin. Repeating the operation for all the bins, we obtain the final differentiable histogram. We apply the same approach to generate the distribution of uncertainty with the same bin centers as for the errors. Finally, we utilize KL divergence loss to enhance the alignment between estimated uncertainties and the true errors. The total loss encompasses the NLL loss and the matching NL loss, which are summed across all resolutions. Let's go to the experiment part. We select GWCNet as the backbone architecture and consider LoveNet along with NLL loss as our primary competitors. We conduct experiments on 3 datasets: SynFlow, VirtualKitty2, both are synthetic data, and Driving Stereo, it's a real dataset. For further implementation details, please refer to the paper. We conduct 2 types of experiments. The in-domain experiment refers to train and test both in the same synthetic data, while the cross-domain experiments refer to train in the synthetic data but test on real data. Here, we demonstrate the strong performance of SetNet while some qualitative results. Comparing the uncertainty maps, especially within the red boxes, SetNet has smaller errors and more accurate uncertainty on SynFlow experiments. SetNet also have better performance on VK2 in different weather, for example, disparity estimation of the faraway street lights. As for the uncertainty estimation, the improvement is more visible, especially under bad weather such as fog or rain. When it comes to the real fortunate day, they often being very dark, the predictions of SetNet are still better. SetNet also overcomes the challenge of the reflections in the water and then captures more faithful details in both disparity and uncertainty maps, such under the bus. We are optimistic that our approach would be similarly successful in other pixel-wise regression tasks. We invited you to explore and utilize our code to further your own research in related problems. Thank you for your interest in our work.